So our book at this point gives us a couple of special integral rules for finding certain types of integrals. So we're eventually going to have a more general way of evaluating these integrals, but for now, just so you can do the problems in the section, we'll give you a few rules for evaluating integrals. So the first one is the integral of a constant. So then rule number one, C is any constant such as 5, -3, 100, whatever it is. If you integrate a constant, the on an interval a b, then the value is simply the length of the interval times that constant. Uh, so uh, let's see. So rule number two, if you integrate the function, just the function x, function f of x equals x, on the interval a b, the value of that is b squared over 2 minus a squared over 2. And if you integrate the function f of x equals x squared on the interval a b, the value of that integral is b cubed over 3 minus a cubed over 3. Let's just do a couple of examples. Well, really one example that demonstrates a few principles here of how those rules might work. So let's evaluate the integral from 1 to 2 of x squared minus 2x plus 5. Forgot the dx, always put a dx at the end. So what I want to do is integrate this using the rules that we know, including the ones that were just on the last page. First thing I want to do is break up this integral. This is going to, using the sum and difference property, this is going to equal the integral from 1 to 2 of x squared dx minus 2 times the integral from 1 to 2 of x dx. I should point out, by the way, that second one, we know that the integral of 2x dx from a to b is equal to 2 times the integral from a to b of x dx. This is this was the constant multiple property from that list of 7 properties. So I'm actually using 2 different properties on this middle term. I'm using the sum difference property to break up the integral, and then I'm using the constant multiple property to bring the 2 outside of the integral. And then finally, this is going to be the integral from 1 to 2 of 5 dx. Okay, so now going back here, we see that we have all the rules that we need to integrate a constant, the function x, and the function x squared. So this is going to be, this first one is going to be b squared, it's going to be b squared over 2, b cubed over 2 minus a cubed over 2. So that's going to be b cubed over 3 minus a cubed over 3. So that's 2 cubed over 3 minus 1 cubed over 3. And then minus 2 times, this is going to be 2 squared over 2 minus 1 squared over 2. Recall that the rule for integrating x is rule number 2. We use b squared over 2 minus a squared over 2. And then plus, we have a constant, the integral of a constant, that's 5, so we're going to use that first rule here. The integral of a constant is going to be b minus a times the constant, so that's going to be 2 minus 1 times 5. So now all we have to do is simplify all this. This is going to be 8/3 minus 1/3 minus 2 times 4/2 minus 1/2, and then plus 2 minus 1 is 1 times 5 is just 5. Simplify this a little bit more, we get 7/3 minus, that's going to be 4 minus 1 is 3. So the 2 is going to cancel, the multiplying by 2 is going to cancel those denominators of 2. So this is just going to be 4 minus 1, and that's 5. So that gives us 7/3 minus 3 plus 5. That's going to be 7/3 plus 2, which equals 13 over 3. And that's the value of that integral. Let's just do one more example that's in negative territory. You'll see what I mean by that in a minute. So let's evaluate the integral from -4 to -2 of x dx. Recall that the integral from a to b of x dx is equal to b squared over 2 minus a squared over 2. So we're going to do that using these numbers. Here we can clearly see that we have a is equal to -4 and b is equal to -2. So we conclude that the integral from -4 to -2 of x dx is equal to, it's going to equal -2 squared over 2 minus -4 squared over 2, which gives us 4 over 2 minus 16 over 2, or 2 minus 8, which equals negative 6. So now you're getting this negative number and wondering, can that possibly be right? And the answer is it is. Let me just show you geometrically why it is. So the function y equals x is just this line, right? So if I put in the numbers negative 2 and negative 4, what I did was I found the area between the curve and the x-axis on the interval negative 2 to 4. So in other words, I found the area of that region. Now, so why is it that I'm getting a negative number if we associate integrals with area? Recall that we're talking about not area for an integral, but assigned area. So areas that appear below the x-axis have to be treated as negative. Therefore, even though if I simply said how many how many square feet of carpet do I need to fill this area, I would certainly be getting a positive number. But the integral is not exactly synonymous with area. It's this notion of signed area, how areas below the x-axis count as negative. So even though the area here is certainly going to be, the actual area is 6 in whatever units we're measuring it in, the integral is giving us a negative 6 because it's treating this area as negative. This becomes even more striking when you realize, for example, that if I write the integral from negative, let's say negative 3 to 3 of x dx, if I do this, I get 3 squared over 2 minus negative 3 squared over 2, which gives me 9 over 2 minus 9 over 2, or 0. If you draw this, you wonder, well, how can that be, that I got 0 for it? Well, here once again is the function y equals x. I'll put in 3, I'll put in negative 3. When I found the integral on that interval, what happened was I got this area here and this area here, and they're equal and opposite. So this is an area of 9/2, and this is also an area of 9/2, but the area on the left, when our integral counts it up, it counts it as a negative signed area. So what we end up doing is we end up adding 9/2 units of positive area above the x-axis right here, with 9/2 units of negative area below the x-axis, and it comes out to 0. So this is actually correct, that if we integrate the function x on the interval negative 3 to 3, we do get 0, even though it encloses what's clearly a fairly large amount of area. It's just that when we fully take into account that areas above the x-axis count as positive and areas below the x-axis count as negative, they balance each other out, and they don't always completely balance each other out. Sometimes you do get a non-zero number if they're not equal amounts of area. In this case, the example that I've done does in fact give us equal amounts of positive and negative signed area, so the integral comes out to 0.